Alright, I want to show you guys today how to do electron configurations and spin diagrams. This will make a lot more sense if you've already done that electron address POGL. It'll really help you to do this stuff because all I'm really showing you is where all the electrons are for an element. The idea of a principal quantum number is basically just what level the electrons are in. So that's what we're talking about when we say what is the principal quantum number. And again, the closer you get to the nucleus, the lower the energy level. So electrons would love to be in the lowest energy level possible. So level 1 would be closest to the nucleus, and level 3 obviously would be further away. So also, each level is divided into sublevels. A level, when you talk about electron configurations, you can use the analogy of meeting someone at a football game. And if you tell them what section you're in, let's say you're going to a Texas or an A&M game, you tell them what section you're in, that's a general area that you're at. That would be like a level. So a level is a general area where electrons are around the nucleus. The lower the level, the closer they are. Then if you tell somebody, well, I'm in section 25, row 5, the row would be like a sublevel because that's specifically how far electrons are away from the nucleus. And the row you're in tells somebody specifically how far you are away from the field. And then if you say, okay, I'm in a certain section, I'm in a certain row, and I'm in seat 5, the seat would be like an orbital. That's specifically where electrons are. An orbital is an area where you can only hold 2 electrons, one spinning one way and one is spinning the other. So let me show you real quick what can be in each level, up to level 4. So if we know what the energy level is in, the number of sublevels in an energy level is whatever the level number is. So if n is 1, it can only have one sublevel. That's an s sublevel. It's also called an s orbital. And the s, the letter designation, tells us the actual shape of that orbital. An s orbital is round. And so that's all that's in level 1 is an s sublevel. If you want to know the number of orbitals in a level, it's the level squared. So 1 squared is 1. It just has one s orbital in it. And then the number of electrons in a level is the level squared times 2. So 1 squared times 2, level 1 only has 2 electrons. Because remember, if it only has 1 orbital, then you can only put 2 electrons in an orbital. And so that's what's in level 1. Level 2, whatever the principal energy level is, that's how many sublevels it can have. So level 2 has 2 sublevels. It has an s orbital as well. It is round. It's just larger than the 1s orbital. And then it also has what are called p orbitals in them, and they are dumbbell-shaped. So they're dumbbell-shaped orbitals. Now, the number of orbitals in level 2 would be the level squared. So 2 squared is 4. Each level always has just one s sublevel, one round orbital. And so if it only has one s sublevel and it has 4 total orbitals, that means it has 3 p orbitals. And this will always be the case. There's always one s orbital. There are always 3 p orbitals. And again, if you can only put 2 electrons in each one of those, you want to know how many electrons you can put in level 2. That's a total of 8. 2 there, 2 there, 2 there, 2 there. All right, level 3. So level 3 can have 3 sublevels. You have an S, again, which is round. You have a P sublevel, which is dumbbell shaped. And you have D sublevels, which are complex. Some will say cloverleaf, but it's a little bit more complex than that. So that's what we've got in level 3. Number of orbitals in level 3, again, would be the level squared. So 3 squared is 9. There's always an s orbital in any level. There's always, if it can have p orbitals, there's always going to be 3 of them. And then we have 9 total orbitals, and that leaves us, I counted for 4, so that means we have 5 d orbitals. Notice there is a mathematical progression there in the types of orbitals. There's always 1s, 3 p's, 5 d's. You should be able to work from that, and in level 4 figure out how many f's there are. Now, if we're going to know how many electrons we can put in those orbitals, it would be the level squared times 2. So 3 squared is 9 times 2, 18. Because there's 9 orbitals there, we can put 2 electrons in each. All right, on to level 4. Again, can have 4 sublevels, S, P, that should be P, D, and then what are called F there, complex shaped as well. So complex shaped orbitals. The number of orbitals in level 4 is 4 squared, so that's 16 total. There's always 1 s. There's always 3 p's. There's always 5 d orbitals. And so we have accounted for 9, there's 16 total. That means there must be 7 f orbitals. Notice there's always 1 s, always 3 p's, 5 d's, and 7 f's. And then, what are these? These are places where you can hold up to 2 electrons. We can put 2 electrons in all those in level 4. Again, so that's 4 squared is 16 times 2. That's 32 total electrons. So this is showing you what can be in each level, each sublevel and orbital. And so now I'm going to just show you how we can make this into where are all the electrons for any particular element. So let me show you how to do that. This is what's called the off-bow diagram. This is arranging all the places you can put electrons. Like this is the nucleus there. All the places where you can put electrons around an element. And so notice there's 3 rules we have to follow when we say where all the electrons are. And rule 1, off-bow principle, electrons go in the lowest energy orbitals first. What does that mean? If you have let's say we have an element, sodium, that's got 11 total electrons. Where would the first 2 go? Each box represents an orbital where you can put 2 electrons. So the first 2 electrons would go in 1s. And then the next 2 electrons could go in 2s. And then you just move up from there until you get 11 electrons. That would be the electron configuration of sodium. The Pauli exclusion principle is saying you can put no more than 2 electrons in an orbital. Again, each box represents an orbital, a place where we can put no more than 2 electrons. And then Hund's rule is telling you what to do when you're trying to fill equal energy orbitals. And let's say you had 3 electrons to put in there. Electrons repel each other, so you can put 1 in each orbital. You don't put 2 in the first and 1 in the second. These are all equal energy orbitals. So again, let me show you real quick how to do a quick electron configuration for sodium. So of course, we're going to follow these 3 rules. So here's how you write them out. First thing you do is you write the level you're starting with, 1, and the sublevel designation. And then right above that, you write a superscript indicating how many electrons you can actually put there. We can put 2 electrons in that orbital. This, again, is not a math problem. We're not squaring all of this. We're simply saying level 1, the s orbital has 2 electrons in it. The superscript number is the number of electrons you're placing, and that total should equal the atomic number, which would also be the number of electrons for that element. So now we've placed 2 electrons for sodium, and you move up to the next highest, next low level orbital. We fill up the lowest levels first, and we fill up the next one. 2, we can put only, there's 1 orbital there, we can only put 2 electrons in that. Then we move on to the next one, 2p. So we'll write down 2, that's the p orbitals. Now you have to remember, this is something you're just going to have to know. There are always 3 of those. Now the number of electrons we can place in them is 2 there, 2 there, and 2 there, for a total of 6. So again, what does this mean? This means level 2, the p orbitals have a total of 6 electrons. Count them up across the top. How many electrons have we placed for sodium? That's a total of 10. It's got 1 more electron. Where does it go? The next one up, 3s. And there's only 1. We can put 2 there, but there's only 1 in that orbital. So you put an electron there, and again, that's the electron configuration for sodium. That's how you'll do them for all the elements. It is repetitive because every single element, the first 10 electrons are going to be there. And so it's not as difficult as you might think. All right, just need to remember sublevel shapes. You need to write these in. That's round. S is always round. P are always dumbbell shaped. D and F are complex. Something you need to know there. Again, you should have gotten that also from that POGL that you worked on. And then maximum number of orbitals in each sublevel. Remember, there's always 1 s. There's always 3 p's. There are 5 d's and 7 f's. Now, this, if you had to try to remember this, and you had to, to know where all the electrons are, that would be a difficult thing to do. Fortunately, you don't. This is what you'll always be given on a test. This is called the diagonal rule. And so this is just that off-bow diagram arranged for you in an easy way. You don't have to memorize this. This will always be set up for you. And this is just showing you how to fill up electrons. If you go back to our sodium again, this is telling you, first of all, this is the lowest energy orbital first. How you fill them up, again, we're going to place 11 electrons again. You'd go 1s2, fill them up, go back to the next line, fill up 2s2, go back to 2p, 2p6, and the next thing you fill up is 3s1. And so, again, that's arranged for you as well, same way. So that's how you do electron configurations for those. I'm going to pick this up with actual configurations with another video, because I'm afraid this one will not, actually, I won't be able to save it if it's more than 10 minutes.